Hello everyone, welcome back to this channel. In today's video, we conclude the method of undetermined coefficients. This is part 3 of this method. We have already learned this method in the previous two videos, and this is just a miscellaneous set of problems based on this method. So let's quickly go through these problems one by one. The first question is determine the appropriate form of the particular solution. So this question is only expecting you to set up the trial YP without really going into calculating the undetermined coefficients. So look at this. The differential equation given to us is y double dash plus 6y dash plus 13y equal to this. So quickly we'll find out yc first. The characteristic equation is r square plus 6r plus 13 equal to 0, which on solving gives us this. Now to set up the trial YP, we must know whether it's a simple situation or a special case. Now since minus 3 plus minus 2 iota is a set of roots, a pair of complex roots which has got something to do with the right hand side, because we know that this complex pair corresponds to a term of the type e to power minus 3x cos 2x and a term of the type e to power minus 3x sin 2x, and one of these terms is appearing on the right hand side. So this is not a simple case, it's a special case, and the pair of complex roots has got multiplicity 1, so it's a special case which is affected. The right hand side term is affected with multiplicity 1, and hence instead of the normal trial YP, we are going to, instead of writing the trial YP for e to power minus 3x cos x, we are going to multiply this with x and then write our trial YP, and hence our trial YP is going to look like e to power minus 3x a x cos 2x plus b x sin 2x. And when we take the derivatives, then we will not get any other term apart from e to power minus 3x cos 2x type term or e to power minus 3x sin 2x type term, which is already in YC. So to avoid duplication, as we saw in the previous videos, we just consider this as our trial YP. And the question is not asking you to find out A and B, it's just telling you, it's just asking you to set up the appropriate form of the particular solution without going into calculation of the coefficients. So that's the end of this part. Look at the second question. The second question, characteristic equation has got three roots, 0, 0 and minus 1. So 0 has got multiplicity 2, so this activates special situation 1, and let's see whether minus 1 has any role here or not. Minus 1 corresponds to e to power minus x, and there's no term corresponding to e to power minus x on the right hand side. So minus 1 is a simple root, it's not a special root, but 0, 0 is special case 1. So instead of writing the normal trial YP for 3 e to power x plus 4x square, we are going to integrate the trial YP twice, because 0 has got multiplicity 2 in this case. So instead of writing for e to power x, we are going to consider the terms which arise out of the integration of e to power x done 2 times. But since the integration of e to power x done 2 times does not lead to any other term, because integral of e to power x is e to power x only, so this remains unaffected even after applying special case 2. Now look at 4x square. 4x square, the normal trial YP for this would have been ax square plus bx plus c, but when we integrate it twice, we land into bx4 cx cube ex square, and the reduced powers also, but reduced powers need not be considered because they are already appearing in YC, so we avoid them because otherwise it will be unnecessary duplication. So this is your trial YP, and when you substitute the values in the given equation and you solve for A, B, C, E the usual way, you get the values of A, B, C, E like this, and hence your general solution, which is y equal to yc plus yp, looks like this. Moving on to the next part, it's an initial value problem. So let's see, what do we do in initial value problems? Initial value problems have a tail attached to them. So there is some extra calculation which you are expected to do. You need to find out the unknown constants C1 and C2 also in the end after imposing the initial condition. So let's look at the characteristic equation first. 1 and 2 are the roots. 1 has got nothing to do with e to power minus x or cos 3x. Similarly, 2 has got nothing to do with these two terms. So it's a simple case. It will just be a simple case. Coming from the simple table, you will be setting up your trial YP as the normal trial YP. For 3 e to power minus x, it's going to be a e to power minus x, and for 10 cos 3x, you will be taking b cos 3x plus c sin 3x, and then putting the values of the constants and then evaluating them. This is what your YP looks like, and hence the solution is given by yx equal to this. This is the general solution. But wait, this was not just a simple differential equation, it was an initial value problem. There were two conditions also attached with the question. So you have to do some extra work here. You will have to use these two conditions to find out the values of C1 and C2. The first condition is y at 0 is 1 and the second condition is y dash at 0 is 2. So when you impose the first condition, you get a constraint on C1 and C2 like this, and when you impose the second condition on y dash, this is how from y you'll first calculate y dash and then impose the condition to obtain the second constraint on C1 and C2. So this becomes a pair of two equations in two unknowns C1 and C2. You solve for them, and after putting the values of C1 and C2 in the general solution here, you get the required particular solution like this. Moving on to the fourth question, it's y double dash plus y. So the characteristic equation has got a pair of complex roots plus minus iota, and we know that plus minus iota is related to cos x and sin x, and cos x and sin x, both of them are appearing on the right hand side. And since this pair has got multiplicity 1, so instead of writing for sin x, you're going to write it for x sin x, and instead of writing for x cos x, you're going to multiply with one more x, because cos x is also affected, sin x is also affected, by multiplicity 1, because this root plus minus iota, this complex pair has got multiplicity 1 here. So instead of sin x, you write it for x sin x, which is ax cos x plus bx sin x, and for x cos x you take c x square cos x plus e x square sin x. And when you take the derivatives, they will be already covered in these terms, because when you differentiate x square cos x, you either get terms of the type x sin x, x cos x, sin x or cos x, which are already either appearing in yc or they are already making their appearance in the trial yp because of the other term. So you don't have to bother about them. You can always avoid duplication. If something is a term of that type is already appearing in yc, you don't have to bother about writing it in trial yp. And if any other component, any other term of yp is already incorporating such terms, then you can avoid them, because ultimately you will be combining the constants. So try to write even if you write unnecessary constants, you will be combining them in the end. So try to avoid writing unnecessary constants right from the beginning here. So basically the idea is to look at the nature of the terms and set up your trial yp, and after putting the values here in the given equation, you can easily verify that your yp looks like this, and hence the general solution is yc plus yp. Now let's look at the fifth question. It's given in the operator notation. D is the operator which stands for d by dx. We have done such questions earlier also. Here the characteristic equation is directly obtained by replacing d by r. So your roots are 2, 2, 2 and a complex pair plus minus 3 iota. Here also in this question, you are not expected to calculate the constants. You just have to set up the appropriate trial yp, because otherwise the calculations will be way too long. So let's see. 2 to 2 has got multiplicity 3 and it affects e to power 2x. So e to power 2x is making an appearance on the right hand side. So for this term, instead of normal trial yp, you will have to multiply it with x to power 3 and then write your trial yp, because 2 is appearing thrice. So you'll have to have an additional x to power 3 here for guessing your trial yp. And plus minus 3 iota is also appearing as a complex pair once. The multiplicity of this pair is 1. So instead of x sin 3x, you'll be writing for x square sin 3x, and hence you're modified. First you write your ycx the normal way, because 2 is appearing thrice. So this is your yc component corresponding to 2, and this is your yc component corresponding to this complex pair plus minus 3 iota. When you write your trial yp, since 2 is making an appearance thrice in the complementary function or the characteristic equation, so e to power 2x, the term e to power 2x into x square gets multiplied with one more power of x, which is x to power 3, because x2 is appearing thrice here. So that makes it ax5 e to power 2x and the reduced powers. Further reduced powers have been intentionally omitted here because they were already making an appearance in yc. So it will be unnecessary to write them again, because in the end the answer is yc plus yp. So avoid duplication in yp with the terms which are already appearing in yc. So this is the contribution that you have for x square e to power 2x, which is modified x to x5 e to power 2x for obvious reasons, because 2 was appearing thrice in the characteristic equation. Similarly for sin 3x, since plus minus 3 iota is a complex pair coming once, so instead of x sin 3x, you're going to write it for x square sin 3x, which becomes ex plus fx square cos 3x, gx plus hx square sine 3x, and the reduced powers will already be there. The cos 3x sine 3x terms will already be making an appearance in yc. You don't have to write them in yp again. And imagine if you were to calculate a, b, c, e, f, g, h, it would have been a big task here because the order of the equation is 5. So if such questions come in the final exam, they'll be just, you know, about setting up the appropriate form of the trial yp without actually going into the calculation of the constants. So that's about undetermined coefficients. Now let's have a motivation for the next video also here. Consider the situation in which you know, setting up the trial yp would not be possible. We have in the previous 3 videos, the previous 2 videos and today's video, we have learned method of undetermined coefficients, which is all about guessing your trial yp. But guesses are not always possible. If the right hand side is not a nicely behaving function in terms of derivatives, then it will be very difficult for us to make a guess. For example, if we consider this equation y double dash plus y equal to tan x, then its characteristic equation will be r square plus 1 equal to 0. So r is plus minus iota. So your yc will be c1 cos x plus c2 sin x. Now what would you guess for tan x? Tan x has infinitely many linearly independent derivatives. There is no pattern as such. The first order derivative of tan x is sec square x. Then you differentiate, you get this, and then you get more complicated terms every subsequent step. So there is not a finite linear combination that can be used as a guess trial yp. So in such situations, we get stuck and we are unable to adopt the method of undetermined coefficients for guessing our yp. So we'll have to switch to the alternative techniques that we have for finding our yp. We know that for non-homogeneous equations, y is given by yc plus yp. Alright. Now y is given by yc plus yp. Yc is easy. You just consider the associated homogeneous equation, characteristic equation, and so on, and you guess your yc. yp, if guessing your trial yp and using undetermined coefficients is possible, you do it that way. But that will not be possible every time. For example, in tan x, it's not possible to make a guess of trial yp. So in such situations, we'll not be using the method of undetermined coefficients. We'll be using the method of variation of parameters for finding yp, which we'll be learning in the next video. So that is all about this video. I hope you have understood this technique nicely. Let's catch up again for the next method in the next video. Thank you so much for watching.